So now we are going to study a particular type of motion, is motion with constant acceleration. In this type of motion, the acceleration doesn't change. It's the same all the time. So here we have an example of a motion with constant acceleration. We have a rocket, right? And these red dots, they represent the motion diagram of this rocket. The velocity versus time graph is a straight line because it's constant acceleration. So if you do the rise here over the run, you get the acceleration, right? The acceleration, so this rise is 27 meters per second, right? So that's delta V, which is 27 meters per second. This run is delta T, which is 1.5 seconds, so that gives you 18 meters per second, or 80 meters per second every second. 80 meters per second squared, so that's what I meant to say. So that is motion with constant acceleration. Remember, the velocity versus time is a straight line. So let's do some algebraic manipulation here. So remember the definition of acceleration, which is delta V over delta T. But delta V is final velocity minus initial velocity. So delta V, remember, is Vf minus Vi, right? So now we can write, then we can rearrange this equation. So let's write it here. Acceleration is equal to Vf minus Vi, which is delta V divided by delta T. So now we know we can take this delta T and put it here multiplying, so we can write this as delta T. So we can write as delta T A is equal to Vf minus Vi. And then we can rearrange this equation and write that the final velocity is equal to the initial velocity plus the acceleration times delta T. And this is the first equation that we are going to use to study motion with constant acceleration, which is this equation here. So now let's try to derive another equation that is important. So remember, from the velocity versus time graph, we can also calculate the displacement that an object moves. For instance, here, if an object moves from this time to, during this initial time to this final time, the distance that the object moves is this area here, this blue area, which is the area underneath the velocity versus time graph. So the area under the velocity versus time graph gives you the displacement on that time, during that time that the object went. So let's see, we have this triangle here plus this rectangle here. So let's see what the area of those two things are. So the area of the triangle is what? Is A delta T, which is this thing here, multiplied by the base, which is delta T, right? And divided by 2. So that is the area of this triangle. The area of this rectangle, that is what? That is VI, right? VI, which is this length here, times delta T, right? So then the total area is what? The total area is VI delta T plus A delta T squared divided by 2. So then we can say that the displacement, right, XF minus XI, right, the displacement is equal to VI delta T plus A delta T squared divided by 2. Or the final position is equal to the initial position plus VI delta T plus A delta T squared divided by 2. So that is the second equation that we need to remember. So we have these two equations, and actually you don't need to memorize these equations, but you need to be very familiar with them. You need to know how to use them. You need to know how to recognize them. And if you read a problem, you should know which equation to use. So there is the third equation that we can obtain, and it's this one here. And this we can obtain by combining the previous two equations. For instance, we know that the displacement delta x is equal to vi delta t plus 1/2 a delta t squared. But we also know that vf, right? vf is equal to vi plus a delta t. So I'm going to get delta t from this equation and plug it in here. So delta t is equal to vf minus vi divided by a, right? So now I'm going to take this delta t and put it there. So I get that delta x is equal to vi delta t, but delta t we said it was vf minus vi divided by a, right? So that's delta t plus 1/2, and now I have an a here, and delta t squared, so this is vf minus vi squared divided by a squared, so that's delta t squared. So now I can simplify this, and I'm not gonna go through the whole algebra here, but you can simplify this, so you would get delta x is equal to vi, so you would get vi vf over a minus vi squared over a plus, then you get 1/2, and then you get a, then you're gonna get vf squared over a squared minus 2 times with the 1/2 they cancel, so I'm going to get vf vi over a, and then finally I'm going to get 1/2 of vi squared over a, right? So now these guys here, this guy and this guy, they cancel, and then here I have a vi over a vi squared over a, and I have a minus vi squared over there, so I can combine these two, and then what I'm left of is this equation, which reads that vf squared is equal to vi squared plus 2 times a delta x. So now we have three equations. We have three equations that we can use. We have this first equation, which I'm going to rewrite here. It says the final velocity is equal to the initial velocity plus the acceleration times the delta t. So we have the second equation, which is the final position is equal to the initial position plus vi delta t plus 1/2 a delta t squared. And finally, I have vf squared is equal to vi squared plus 2 times a delta x. So now, these equations that you have here is all you need to solve the motion with constant acceleration. And so you're going to get a lot of practice doing that, so you need to be very familiar with these equations, and by doing the problems you'll hopefully develop an understanding on what to use and when to use any one of these equations. In following videos we'll be doing practice on that.